Welcome to Algorush. Today, we're going to pull back the curtain on something amazing, the engine that powers almost every modern database.
So, you ever wonder how that works? How does a database find one specific record, like your user profile, out of literally billions of others, and do it in an instant? It feels like magic, right? But it's not. It's just some seriously clever engineering.
And the secret sauce? It's a data structure called the B-tree. This thing is the quiet, unsung hero behind the incredible speed of pretty much any database you can think of. So what's its trick? How does it pull this off? Well, let's dive in and break it down.
All right, Section 1, the perfect index. First things first, we've got to understand its main job, finding stuff, and finding it fast. So how does it actually navigate its own structure? So at its heart, what is a B-tree? Think of it as a special kind of filing system, one that's designed to keep data sorted and make searching, adding, and deleting things super efficient. We're talking logarithmic time here. But the real magic, the absolute genius of the B-tree, is in how it stays perfectly balanced as it grows and shrinks. We'll get to that.
Every single search, no matter what you're looking for, starts at the exact same spot, a single root node at the very top. It's like the front door to a giant, perfectly organized library. You always start at the front door, and from there, there's a clear path to any piece of data you need. And the lookup process itself, it's actually pretty simple. You start at the root. Inside that node, you do a quick binary search on the keys stored there. Find the right range. That search points you to the exact child node you need to visit next. So you follow that pointer down one level, and you just repeat the process. Binary search, follow the pointer, over and over. And because these trees are super wide and not very deep, you can go from billions of records to the one you want in just a handful of steps. It's incredibly efficient.
Okay, Section 2, structural integrity. Now, finding data is one thing, but what happens when we add new data? Because, let's be real, data is never static. So how does a B-tree grow without just becoming a complete mess? That's where overflow comes in.
Yeah, this is a huge deal. See, each box or node in the tree has a limit. It can only hold so many keys. So, what happens when we try to shove just one more key into a node that's already completely full?
That exact situation is called a node overflow, and the B-tree has this really elegant built-in way of handling it. It doesn't throw an error or crash. Nope, it just performs this clever little operation called a split. So here's what happens. When a node gets too full and overflows, it literally splits in half. You get two new nodes, each about half full. But then, and this is the really important part, the median key, the one that was right in the middle of the original full node, gets promoted. It moves up to the parent node. It's now the signpost that tells the database which of the two new nodes to go to.
And this is how B-trees grow from the bottom up. A split at the very bottom can push a key up, which might cause the parent node to get full, and split, and that can bubble all the way up the tree. This bottom-to-top construction is the magic trick that lets the tree get bigger while keeping everything, and I mean everything, perfectly balanced.
All right, Section 3. So growing is one half of the equation. But what about the other side? We also delete data. How does a B-tree shrink back down without becoming all sparse and inefficient? This is where we talk about underflow. Right. What about the opposite problem? If you keep deleting keys, a node can get, well, nearly empty. And that's just as bad as being too full. It's a waste of space, and it means more work to find things. The tree needs a way to tidy up and stay efficient.
Yep, you guessed it. This is called node underflow. When a node gets too empty, when it drops below a minimum number of keys, it triggers a cleanup routine to keep the whole structure dense and fast.
So to fix this, the tree has a couple of options. First, it tries to be neighborly. It'll try to borrow a key from one of its siblings, a process called redistribution. But if its neighbors are also running a little lean, it goes to plan B. It merges. The nearly empty node will actually combine with a sibling to become one single healthy node again.
And this merge operation, it's pretty much the exact opposite of a split. Instead of promoting a key up, a merge pulls a key down from the parent to fuse two nodes together. This is what keeps the tree tidy and compact. It makes sure every node is pulling its weight. No wasted space, no slow searches.
Okay, let's wrap this up in our final section, the balancing act. When you put all these pieces together, you see that a B-tree isn't just a static diagram. It's more like a living blueprint, something that's constantly adapting.
And it's all about this incredible balancing act. Look at this comparison. On one side, you've got growth. You insert data, you get an overflow, and the tree splits to grow upwards. On the other side, you have consolidation. You delete data, you get an underflow, and the tree merges to shrink. It's this constant push and pull, this perfect equilibrium that makes the whole thing work.
So what this really means is that a B tree is a dynamic, self-regulating structure. You don't have to manually go in and rebalance it. It just gracefully adapts to whatever changes you throw at it all by itself, thanks to these simple rules of splitting and merging.
And that is why this all matters. This constant balancing act is the secret behind why databases are so unbelievably fast and reliable. It guarantees that the journey from the top of the tree to any piece of data is always short, always efficient. Always.
So, the next time you search for something online or log into an app, just take a second to think about the incredible, elegant dance of splits and merges happening under the hood. It really makes you wonder, right? How many other invisible, perfectly balanced structures like this are out there?